So let's continue with our study of vectors that depend on a single variable. So we already saw how we can do integration of vectors in this case. And next we are going to see how to do differentiation of vectors. So let's get to it. The differential of a vector, dv over du, where u is a variable such that this vector depends on u. Okay? So it is very easy to define by applying linearity. So let us write it here. So our vector w is equal to dv over du, which is equal to d over du of vector v, which in general can be written in a certain basis, right? So it can be v1 times a basis vector e1 hat plus v2 times basis vector e2 hat plus vn times basis vector en hat. So now if we apply the linearity of the differential operator, linearity of differentiation, and also assume that the unit vectors are constant, such as, for example, x hat, y hat, and z hat, they are constant. Then we arrive at the differential of the first component of v times e1 hat plus the differential of the second component of v times e2 hat plus the differential of the nth component of v times en hat. Okay? Now if we were to write this in a notation of vectors, then this means that if vector v is our vector column written as a column v1, v2 up to vn, that's how we write vectors, as a column, then when we apply the derivative dv with respect to u, then the result is this vector w, which is simply a vector. Remember, the derivative of a vector is also a vector, and the components of this vector are simply the derivatives of each of the components of the original vector. So this is very easy to understand. Now let's talk about the interpretation. Or even before talking about the interpretation, let's talk about the definition. How do you define the derivative of a vector? So this is how it's formally defined. The derivative of vector v with respect to a variable t is equal to the limit when delta t goes to 0 of vector v evaluated at t plus dt, at t plus delta t, minus the vector evaluated at t divided by delta t. Okay, this definition should really ring a bell because it is identical to the definition of the derivative of a function f of x, just substituting if f was here, f a scalar function, then this would be f of t plus delta t minus f of t, right? So the definition is identical. But what does it mean visually? So let's imagine that we have a three-dimensional space. X, y, z. And then we have a vector v that depends with time. Okay, so vector v is a vector that is changing with time. So this vector at time t is equal to this, so this will be v of t. And then after some time, this vector has changed. Okay, so now we have a vector which is v of t plus delta t. Okay, so then the operation of this subtraction, vt plus delta t minus vt, what is that? So this subtraction is simply the difference between these two vectors. So let me draw it here. So this vector here, this vector is equal to v t plus delta t minus v of t. Okay? Now what is the meaning of this? Okay, let's imagine I plot the vector v of t, but instead of plotting it only at time t, and at time t plus delta t, I plot it at all times. So I watch how the vector is moving, okay? So then this vector will be tracing some sort of path, okay? Maybe something like this. It's tracing a path, yeah? So as you change t from one moment to the next, you are moving the tip of the vector through this path, okay? So then what happens when delta t tends to 0? So when delta t tends to 0, this means that we are increasing time by a smaller and smaller amount. So we are getting a vector closer and closer. So that this v of t plus delta t minus v of t tends to be more and more tangent to the line. But it's also becoming shorter, right, as delta t tends to 0. However, fortunately, we are dividing by delta t. Therefore, there is a limit in which at the limit, the vector becomes a vector that is exactly tangent to the line that was being traced by vector v of t. Okay? So the numerator is becoming smaller and smaller, but the direction is becoming tangent to the line, while the denominator, which is a scalar, is also becoming smaller and smaller at the same rate, so that in the limit of doing this division, you are getting a vector which is pointing tangent to the line. Okay? And also the length of this vector is of course proportional to how fast this vector v is moving as we are changing the parameter t. Okay? Excellent. So that's a very, very important thing to realize, that the derivative of a vector is equal to a tangent vector to the path. Okay? So imagine we have a path, a position vector r, which depends on time. Okay? And this is describing the path of some particle. And for this, I have an applet. Let me switch to that. So I have this Mathematica applet, and see how this begins. I define x, y, z as functions of some parameter u. Okay? And these are just functions. 1/4 times the sine of 3 pi u plus u over 10 minus u. Okay? They are just functions of u, x, y, z. And then I define my vector r having these three components, x, y, z. Okay? And then I define the vectors that are the derivative of vector r with respect to u, and then another vector which is the derivative of this derivative. So that this is like the second derivative. So I'm going to show you how this looks. So if we go to the plot, here is the plot. So here you can see our xyz axis. So this is our origin. And then here I have a slider t, which when I move the slider, the blue vector is changing. Okay, and this blue vector represents r as a function of the variable t. Okay, so even though in the code the name of the variable was u, for the plot I decided I just renamed the variable to t. So you can imagine that as time passes, so I can actually click this on play. So as time moves on, the vector is changing. Okay, now let me plot the derivative of this vector, of this blue vector, with respect to time. And now this is this red vector here. Please remember that this path is in 3 dimensions. Okay, so now I plot this red vector, and if I play time now, you can see that the red vector is always tangent to the curve. Okay, it's not very easy to see from this perspective. Let us see it from here. So the red vector, which is the derivative of the blue vector, is tangent to the curve. And this makes sense because you know that the velocity is the derivative of the position vector, right? So that makes perfect sense. Now, what maybe is not so intuitive is what happens if I take the derivative again. So if I take the derivative again, I have this tick here, and I get this green vector here. Okay? So what is this green vector? So this green vector, let's play time. So this green vector is pointing in the direction in which the red vector changes. Okay? So this is the acceleration. So you can see that whenever there is an acceleration, the red vector changes in that direction. Yeah? So if the acceleration is to the right, the red vector is tilting to the right, and when the acceleration is to the left, the red vector tilts to the left. But then you may ask, but Paco, you just told us that the derivative of a vector is a tangent to the path of that vector. But here, the green arrow, which is the second derivative, is not tangent to any path. So what is going on? And that's because the derivative of a vector is tangent to the path followed by that vector when you place the starting point of the vector in the origin. So our red arrow here, I'm just placing it, I'm placing the starting point of the red arrow at the tip of the blue arrow. Okay, so I'm placing the velocity at the current position r. However, what happens if I get this red velocity vector and I put it at the origin? So this is what I can do here. Okay, so now this same vector that I have here, I'm placing it here. Okay, so now when I change time and the red vector is changing, I am just copying that vector into the origin. Okay, you can see it clearly here. So the velocity is here and I'm copying it, putting it into the origin. So now you can imagine that this velocity vector is tracing another path, which is this red path here. Okay, so notice that as we play, this red vector is tracing this path. Okay, and now the acceleration, which is the green vector, is tangent to that path. Okay, so that explains it. So always the derivative of a vector is always a vector tangent to the path that this vector is tracing, but only when you put, of course, the vector in the origin. Okay, so that is what I'm trying to show here in the notes. So if you have the position vector, then the velocity vector, which is tangent to the path of rt, is given by the derivative. Okay, and then the acceleration a of t would be tangent to the path of v of t. Okay, if you actually plotted it. So this path is not plotted in this figure. Okay, so you can see that differentiation of vectors is really useful. It can be done in mechanics to find velocity and acceleration in terms of position vector, but also it can be used in pure mathematics when we just want to find the tangent to a curve. So if you can write this curve as a vector that depends on some parameter, then you can always find a tangent to the curve by doing the derivative. Okay, thank you for watching.